All right. Sometimes you want to find the actual size of a sample space without actually listing out the entire sample space. Because total number of possible outcomes gives us the denominator of pretty much any probability question related to that situation. So we're just going to kind of build it up from here. They tell us that one flip, and flipping a coin, one flip leads to 2 outcomes. So, all right, that is bright. Flip outcomes. We have one flip gives us 2 outcomes. 2 gives us 4. 3 gives us 8. All right, we want to know, is there a pattern? Well, yeah, otherwise I wouldn't ask. So why don't you tell me how many outcomes would there be for 4 flips?
Wait.
16. All right. Dot, dot, dot. What if I have n?
2 to the n.
2 to the nth power, exactly. 2 to the n. All right. Because in each case, all we're doing is taking the 2 outcomes for any one trial and raising it to a power that's equal to the number of trials. All right, so we could do the same thing with dice. So this time it's rolls and outcomes. So one roll gives 6 outcomes, 2 gives 36, 3 gives 216. And for n rolls,
6 to the n.
6 to the nth power. So the general formula is really just going to be, and I'm going to just not overly generalize it in terms of symbolic notation, but it just boils down to number of outcomes per trial and that's going to be raised to the number of trials. All right, but the important thing to think, or to consider anyway, is that this only applies for what we call independent events. And what I mean by that are events whose probabilities that don't change from trial to trial. Like you flip a coin 30 times, any one of those trials, the probability of getting heads is still 1 out of 2. All right, but if I withdraw a card from a deck and then don't put it back in the deck, it has impacted the overall probability of selecting some other card. All right. It may not impact the number of the other type of cards, but it'll impact the overall number of available cards. So it will have some kind of impact. All right. So that's where I'm going to call it at this point. Work at our own pace sometimes, I guess. So anyway, addition rule. So addition rule is pretty simple. It's the rule of OR. It's the probability of a single trial, or in a single trial, key ingredient there, of either of 2 events occurring. So we'll start off with a simple case involving a deck of cards. So a deck of cards, the sample space is in one of the previous pages. One of the easiest ways to handle a question like this is to just look at that sample space. It says a card is selected from a standard 52 card deck. Determine the probability of either a 7 or an ace being selected. All right, so all I'd be looking for when I'm looking for the probability of getting a 7 or an ace would be the unique cards in the deck that are either 7 or ace. And how many of those are there? 8 of them, right? So you could jump right to that and say 8 out of 52. All right. If I draw a Venn diagram, we have the set of aces, and we have the set of sevens. There's no overlap between the two. All right. So that tells me that I can take the probability of getting a 7 and add to it the probability of getting an ace. Since each one of them is 4 out of 52, there's 4 of each card in the deck, then we get a total of the 8 out of 52, and that's the end of it. All right. Now, a proper Venn diagram can be kind of aggravating, because what you need to do is include all of the probabilities in your diagram. So for aces, I would note that it's 4 out of 52. For sevens, I would also note that it's 4 out of 52. All right. Everywhere else in the box is the set of cards that are neither 7 nor aces. So not 7, well, I'll write probability. Not 7 or ace. And that's going to be everything else. All right, a proper sample space would deal with every single possible outcome in the entire set, and the Venn diagram deals with the sample space. It's a visual representation of that sample space. So not a 7 or ace means the same thing as neither a 7 nor an ace. All right, so 52 cards overall. Subtract 8 from that, you're talking about 44 out of 52. All right. So if a question on a test asks you to create a Venn diagram, you have to have all those ingredients there. Second example, probability of getting a 7 or a red card. All right. So if I follow the same approach from the previous question, I'd say probability of 7 plus the probability of red. There's more to it than that, but it's a place to start. How many 7s in the deck?
4.
How many reds?
26.
26.
I was thinking
Only like the diamonds or the heart, yeah. All right, but when I count my 7, all my 7s, I have my 7 of clubs. That's not a club. 7 of spades, which is the way I draw it, an upside down heart. 7 of hearts, and 7 of diamonds. So in the process of counting all my 7s, I double counted a couple of reds, right? Because when I took all my reds, I included the red 7s, so I'd have to subtract those off, all right? So what I would need is a subtraction of the probability of getting a card that's 7 and red at the same time, all right? So 7 and red. All right. This is a symbol for intersection. It means and. All right. So the symbol for or is actually a U, all right, or a union. You might know that from domain and range and things like that. Very rarely did you work with the intersection, all right, but it's basically an upside down union symbol, all right. So it's shorthand notation, sure, but it's also some notation that you could end up seeing on the AP exam. You see it on your on the note cards, the AP note cards. This is the notation that they use, so we want to be familiar with it. So long story short, we want to subtract off the 2 over 52. So instead of getting 30 out of 52, we get 28 out of 52. Now visually, in the form of a Venn diagram, draw it a little bit bigger this time, we'd have our set of red cards, which is a lot. Then we'd have our set of 7s, which is not as much. And then we'd have our overlap, which is the set of red sevens. All right. So we could just label our probabilities in here. For the reds, we knew that there were 26 out of 52. For the sevens, there were 4 out of 52. I'm sorry, only the sevens, but not red at the same time, would be 2 out of 52. And then the red sevens, the probability of that would be also 2 out of 52. All right, so then the probability of getting neither a red or 7 would just be 52 minus 28. So 24 out of 52. All right, so that's our probability. Well, we had a probability answer, but these are all the possible probabilities associated with this situation. All right, you got to be prepared to include all of it. Now, there are names for these. The first case is known as a mutually exclusive situation. Mutually exclusive. Also known as disjoint. All right, there's no connection between the two sets.
Just when you did that Venn diagram on the bottom right, for the sevens you only put 2 out of 52, and for the reds you did 26. So why didn't you include the? You see, what I mean, like there's 4 sevens, but you didn't include the red ones, but for the reds you did include the.
Because, sorry. The overlap is the case where you're dealing with cards that are both red and 7 at the same time. The part where it's just the sevens is implying that it's 7 but not red.
Oh, okay.
So then you would only be talking about the 7 of clubs and the 7 of spades.
But the reds, wouldn't that be the ones that are red and not 7?
Oh, thank you. I thought you were talking about the other part. Yeah, I whiffed on the red component. Thank you, thank you. So that's 24. Ooh. So then, oh, the other number is shockingly fine though, right? The 24 out of 52 for neither red nor 7? Okay. All right, so that gives you the general addition rule, which is basically a formulaic approach of saying what I was saying on the previous page. In terms of the way the AP likes to write it, A union B is equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. All right. For mutually exclusive events, there's no overlap, so there's nothing to subtract. So it's irrelevant. I don't know why I have so much space there. It's not really necessary. So, not needed. So that's a typo for somebody. Same deal here. All right, so I'm going to pop a star onto this example set because you'll try those on your own. And then I'm going to hop on over to multiplication properties. It's pretty straightforward also. Multiplication rule deals with multiple events. So 2 or more trials are being conducted. Now we're starting off with cards, but we're going to get into contextual situations, so it's going to get a lot more complicated. So, but if we can get the groundwork when dealing with cards, dice, and things like that, then things will be a lot easier. A coin is tossed, and then a die is rolled. Construct a tree diagram for a flip of a coin. All right, so heads, tails. And a roll of a die. and find the probability that you would toss a heads and roll a 5, all right? It's implied that you'd find that from the tree diagram. All right, so if I flip the coin, I could get a heads, but then after I roll the die, I could get any of the outcomes from 1 to 6 on the die. So 1, 2, 3, 4, 5, 6. Same thing for tails. All right, so the first trial, you got to kind of think of the first branch as being the experimenter. You know, I'm flipping the coin, so this is me, the beginning of the tree. I would want to include probabilities for each one of these outcomes. So the probability getting heads would be 1 out of 2. Same thing for tails. All right, the probability of rolling a die, well, it's an independent event, so it doesn't really matter whether I got a heads or tails. The probability of getting a die to come up as a 1 is going to be 1 out of 6. Same thing for 2, 3, 4, 5, and 6. So each one of these has a probability of 1 out of 6. So it kind of stinks because you have to write all these probabilities in anytime you make a tree diagram. Which means that if it were 3 flips of a coin and 3 rolls of a die, well, it would take the better part of the day, I think. So each one of these would have a corresponding probability associated with it. So multiple events means multiplication, because I want the 1/2 to occur first and then the 1 in 6. So I'd be looking at a product of 1 out of 12. And that would be, because this is a uniform distribution, 1/12 all the way through. Now, because it's uniform, you didn't really have to label all these values in order to figure out that it would be 1/12, because if every event is equally likely to occur, then since you have 12 equally likely outcomes, you'd be looking at each one of them occurring 1/12 of the time. All right? So you could get it that way, but only because it's a uniform distribution. If it were not uniform, so let's say it were a dependent situation, where you're dealing with maybe 2 cards being selected from a deck, and you had to make a tree diagram. Then, if you didn't replace the first card before you selected the second one, then the probability of selecting the second one would be impacted by the fact that the first one was selected. All right? So, not the case here, but it could be. And so you'll see that when you get to the examples that follow. But, I mean, in this simple case, it's like if you just needed, for independent events, to find a probability, you just multiply them together, 1 out of 2 times 1 out of 6, and you get 1 out of 12. It's when you have dependent events, that's a different story. All right? So I'm going to pop a star on these problems. So you could try those on your own also. Those are a little bit more interesting than the ones on the previous page, but definitely very doable. And then the last thing, and I'll get out of the way here, is really just me slapping a star just on this whole section here, because I'd rather you try that first on your own before I go over it all with you, because the formula is there. It's just a matter of you seeing if you can figure out a way to apply it. All right. So with